Good afternoon. Good afternoon. Hope all is well and everyone's all right. Oh, got a few more still coming in. Let's let the audio connect. All right. All right. So, once again, good afternoon. Hope everyone's doing okay. If I'm not mistaken, we are in chapter 5. And we did 5.2, so I believe we're at 5.3. Wrong button. So before we do that, any general questions, any concerns, comments before we get in there? All right. So looking at 5.3 today, should be able to do 5.3 and 5.4 today. And then that'll be the sections in chapter 5. So 5.3 is independence and the multiplication rule. So two events are independent if the occurrence of one event does not affect the other. So let me bring the F closer. Two events are dependent if the occurrence of one event does affect the other. So the first exercise, determining whether our events are independent or not. So it says, suppose you flip a coin and roll a die. Are the events obtain a head and roll a 5 independent? So obtaining a head and rolling a die, rolling a 5, are they independent? So in other words, do the events have anything to do with the other? In other words, as far as the probability is concerned, does rolling a die affect flipping a coin or vice versa? So yes, they are independent because flipping your coin has nothing to do or does not affect the probability of rolling a 5. All right. Next one, are the events earned a bachelor's degree and earn more than $100,000 per year independent? Okay. So no, they're not independent because earning a bachelor's degree increases your chance at earning $100,000 or more. It doesn't guarantee that you will earn that much, but it will increase your chance, increase your probability of earning $100,000 or more. So they're not independent. any questions on either one of those? Make sure you're okay. Of course, if I scroll up too far, let me know. All right, so the multiplication rule for independent events. So remember last section, we were doing E or F, the probability that E or F will occur. This time, we're looking at the probability that E and F will occur, that both of them will occur versus one or the other. You know, last section, like I said, we're looking at one or the other occurring. This time, we're looking at both of them occurring. So before we were adding, this time we're multiplying. If we want to know the probability of E and F occurring, we'll multiply those probabilities. So in the game of roulette, the wheel has slots numbered 0, 00, and 1 through 36. A metal ball rolls around a wheel until it falls into one of the numbered slots. What is the probability that the ball will land in the slot numbered 17 2 times in a row? So I'll give you a chance to write that down for those who are. All right, then scroll up. All right, so these events, one thing you do want to establish, remember that when you go back to the formula, this is for the multiplication rule for independent events. For those events that are dependent, you know, we'll take another route. We'll talk about that next section, but these events are independent. The occurrence of rolling a 17 does not affect rolling a 17 again. So it's not like if you roll a 17, then they'll put a space over there to close it out or something to close out the fact that you can roll 17 or decrease the chances. So these events are independent. Rolling a 17 does not affect rolling 17 the second time. So what we want to do now is to find the probability of rolling 17 the first time or just one time. And we know we talked about establishing probability before or calculating probability before. You want to first establish the number that's in your sample space. So notice we have 0, 00, and then 1 through 36. So that's 38 numbers altogether. So that's where we get 38 from. And then it says the event is rolling a 17. Now there's only one 17 on the board. So that's why this is 1. If there were two 17s, then you have 2 there. You know, however many different ways you could get a 17, that's how many numbers you would put right there. Once again, we only have one way of getting 17. So that's why that's a 1. So the probability of rolling a 17 is 1 over 38. All right, questions on that first part? All right. So we have the probability of rolling 17 once. But since they're independent, and if I want to know how to roll 17 2 times in a row, I would take that 1 over 38 and multiply times each other. And I get 1 over 1444. And then pay attention to the directions in my math lab. If they want you to write it as a decimal, that's just 1 divided by 1444. And so you watch the decimal where they want you to round it to. And then sometimes writing it as a fraction is good enough, but they'll tell you, round to the nearest decimal. They'll let you know. Yeah. But either one of those answers should be fine. All right, questions. All right. Everybody done with the blue? Okay, here we go. So the probability that a randomly selected 24-year-old male will survive the year is 0.9986, according to the National Vital Statistics Report. So first question A, what is the probability that 3 randomly selected 24-year-old males will survive the year? What is the probability that 20 randomly selected 24-year-old males will survive the year? So once again, give you a chance to write. All right, scrolling up some. So just like before, you do want to ask yourself, are the events independent? Because that will dictate how you calculate moving forward. So the events are independent. 24-year-old male surviving the year has nothing to do with the next person surviving the year. Well, I guess, of course, unless that one person that survived was coming after the one another person. But under normal circumstances, one person to survive the year has nothing to do with another person surviving the year. So these events are independent. All right. All right. Probability that a male will survive, 9.9986. So the probability that all 3 survive would just be multiplying all 3 of them together. I still copying in black. All right. So 0.9986 cubed, because multiplying it to itself 3 times, that'll be 0.9958. In the blue circle, I'll just point out how you could put it in the calculator if you didn't have the cube button. That hat button right there raises it to an exponent if you've never used it before. So. All right, questions, any questions? Next one, the probability that all 20 would survive. So you just raise that 0.9986 to the 20th power, and that'll be 0.9724. Any questions? I'll scroll up. All right, so this next one is leaning on the same information. Says compute the probability that at least one male out of 1,000 24-year-olds will die during the course of the year if the probability that a randomly selected 24-year-old male survives the year is 0.9986. So give you a chance to write. All right, so we want to know the probability that at least one male out of 1,000 will die, but we have the probability that a 24-year-old will survive. So we're gonna have to use the complement rule in such a way, so in a certain way. So we have at least one person dies is what we wanna know. So what we're gonna do is calculate the probability that none of them will die and subtract that from one. Because you have the probability that none will die. Then you can subtract from one the probability that at least one will die. Because you're saying at least one, that means one could die, maybe two could die, 50 could die, so that covers all the rest. So we found the probability that none will die. That's 0.9986 raised to the 1,000th power. So of course you would throw that in the calculator. And that's 0.2464. Subtract that from one, you get 0.7536. And that will be your answer. All right. Questions. All right, everybody good? All right, so let's look at 5.4. Conditional probability and the general multiplication rule. All right. All right, so conditional probability, we have the probability of F. You have this slash in between E and F. So it has, whenever we see that notation, that's the probability that F occurs given that E has already occurred. So this right here, this positioning matters. F/E means F given E has already occurred. If you were to flip it, you want to find a probability that E given that F has already occurred. So the positioning does matter. So that's the probability that F occurs given that E has already occurred. All right. So here's the formula for calculating the probability of F given that E has already occurred. So notice you have the probability of E and F on top, then the probability of E on the bottom, or you have the number of E and F on top over the number of E on the bottom. So either one will give you the same result. All right, I'll scroll up. So we have a little chart here that we're going to use, depend on. This chart represents the marital status of males and females 15 years or older in the US. And it is in millions. And we're still holding on to the formula. All right. So you have never married, married, widowed, divorced, separated, and then totals. Then you have your males column, 41.6, 64.4, 3.1, 11.0, 2.4, 122.5. Females column, 36.9, 63.1, 11.2, 14.4, 3.2, 128.8, and then your totals, 78.5, 127.5, 14.3, 25.4, 5.6, 251.3. All right, now scroll up. All right, so we're going to use the table to answer the following questions. Compute the probability that a randomly selected individual has never married, given the individual is male. Excuse me. Oh, I thought I went to the problem. Okay, I'll write down the next one. Next one is compute the probability that a randomly selected individual is male, given the individual has never married. So really you're flipping the conditions. All right, let me go up. All right, so I'm going to call N never married and M male just to shorten it up. So we want the probability. The first one is asking us to find the probability that an individual never married given the individual is male. So that's what we have right here in this first notation, the probability of M, N given M. And if we go according to the formula, N and M would be the top number, never married and male. And then the bottom number would be the total number of males. So if we go to the chart, never married and male, 41.6, total number of males, 122.5. And so that's what I have here. And then the decimal value is 0.34. All right. Any problem with that? All right, next one. Same thing, call a male, M, never married, N. This time they want the probability that a person is male given that he never married. So top number is male and never married. Bottom number this time, remember bottom number is always this one, is never married. So if you go up, so male and never married is still this value, but the total number of never married is 78.5. So 41.6 over 78.5, 0.53. So that's the percentage. Well, you could say percentage, that's the chance. Actual percentage would be 53%, but that's the chance that you choose somebody who is male given that is never married. All right, questions. All right, let's scroll up. So here, suppose that 12.7% of all births are preterm. Also, 0.22% of all births resulted in a preterm baby who weighed 8 pounds, 13 ounces or more. What is the probability that a randomly selected baby weighs 8 pounds, 13 ounces or more, given that the baby is preterm? And then is this unusual? All right. So I decided, and you know, when you're doing this thing, in order to shorten things up, you can call it what you want. I decided to call W weighs 8 pounds, 13 ounces or more, and call P preterm. Those are our two events that we're looking at, because you want to know what's the probability that randomly select the baby weighs 8 pounds, 13 ounces or more, given the baby is preterm. So that given lets you know what's before it is your first event, is an event, what's after it is that other event. All right. So we saw that the probability that the baby is preterm is 12.7%. Converted that to a decimal, 0.127. Then the probability that a baby is preterm and weighs 8 pounds, 13 ounces or more. Just make sure I wrote something right. It's 0.22%, and as a decimal is 0.0022. So now we want to know the probability of getting a baby that weighs 8 pounds, 13 ounces or more, given the baby is preterm. So that's what this represents for us. If that's our wordings, we follow the positions of our letters. Preterm and weighs 8 pounds, 13 ounces or more is on top. And then preterm is down bottom. So that's 0.0022 over 0.127. That'll be approximately 0.0173. So I'll give you a chance to finish writing that down. Don't forget, also they asked us, is this unusual or not? So we're not quite finished with this problem, but once again, give you a chance to write it down. All right. So now, as a percentage, that's 1.73%. And it asks us, is this unusual? The answer is yes, because the probability is less than 0.05, which is 5%. So remember, we talked about something being unusual or not. And we said that our standard that we will use is if it's less than 5%, then it is considered unusual. And so that's what we did here. All right, any problems, any problems? Scroll up. All right, so our general multiplication rule, did all that to get to this general multiplication rule. If we want to know the probability of E and F occurring, but these events are dependent, so we will calculate probability of F given that E happens, and then multiply that times the probability of E. So remember, if they're dependent events, the probability of one happening actually affects the probability of another. So once again, probability of E happening, then the probability of F happening given that E has already happened. All right. All right. Are we done with the formula? All right. The probability that a driver who is speeding gets pulled over is 0.8. The probability that a driver gets a ticket, given that he or she is pulled over, is 0.9. What is the probability that a randomly selected driver who is speeding gets pulled over and gets a ticket? All right, let's scroll up. So we want to know the probability of a randomly selected driver who is speeding gets pulled over and gets a ticket. So we can call T gets a ticket P for pulled over. So we have two probabilities given to us. The probability that you get pulled over is 0.8, and the probability that you get a ticket, given that you were pulled over, is 0.9. So you want to know the probability of getting pulled over and getting a ticket, because getting pulled over increases your chances of getting a ticket. That's why they are not independent. So we'll take the probability of getting pulled over, multiply it times the probability of getting a ticket, given that you were pulled over. 0.8 times 0.9 is 0.72. All right, questions? Any questions? All right, I think we got like one more. Pretty good with the red. Hold on, is this the last one? Yeah, thought so. All right, so in a study to determine whether preferences for self are more or less prevalent than preferences for others, researchers ask individuals to identify the person who is most valuable and likable to you, or your favorite other. Of 1,519 individuals surveyed, 42 had chosen themselves. All right, you scroll up. So that was just the intro. Let's look at the first question. Suppose we randomly select one out of the 1,519 individuals. What is the probability that he or she had chosen self as a favorite other? So regular probability problem or question. Our sample space is 1519. Says suppose we randomly select one out of the 1519. What's the chance that he or she had chosen self? So we know out of the 1519, 42 had chosen self. So that probability would be 42 over the 1519. So that's a chance that you would choose or pick one out of that 1519, 42 out of that 1519. Questions on A. All right, we go with A. Right. So B, if two individuals from this group are randomly selected, what is the probability that both chose self? All right. So looking at the probability of the first one you choose chose self, and then the second one you choose also chose self. So probably the first one chose self, and then the second one chose self, given that you already picked out one that chose self. So why does that matter? So when we look at the first one, we already said that the probability of choosing self will be the 42, or getting somebody to chose self will be 42 out of the 1519. Now, if you pick that one person out and then you go to pick another person, well, there's only 41 people left now that actually chose self, because there were 42, but you chose one out. And then also there are 1,518 people left because you chose one out of the total group. That one that you chose from here takes one from the 42 and one from the 1519. So just make sure we're okay with how we got 41 over the 1518. So the bottom number is the total number of everybody in the group. And then 42, the top number, is the people that chose self. So you take one away from both top and bottom. So that's the probability, 41 out of the 1518. And now that you have that probability, you multiply those two fractions together, and you'll get that decimal down there, 0.007468. In the green was just me converting it to decimal and then multiplying them. So it's up to you how you want to do it. Either way, you'll get 0.007428. All right. Questions on that one before we go to C? Make sure we're okay. All right. So last one, compute the probability of randomly selecting two individuals from this group who selected self, assuming independence. So don't forget, independence means that the probability of one occurring does not affect the probability of another occurring. So if they are independent, then the probability doesn't change. It's going to be 42 over 15, 19 in both cases. And you would just multiply those together. That'd be 0.007645. All right, questions, any questions? All right. Let me check something real quick. Okay. Okay, just calculating some things in my mind. Okay. Everybody good? Everybody straight? So that's it for the lectures. New material out of chapter 5. So make sure we are getting into math lab accordingly the way we should be. Trying to check something out real quick before we close this out. Give me 1 second. All right. Okay. So yeah, so we'll pause right here. Make sure though, you guys are getting in there. Don't forget, this is chapter 5. We're done with chapter 5. We know for a fact we're at least going to get to chapter. Got 8, and then it'll do a couple sections in chapter 10. So make sure you get in there, getting this stuff done. You want to get your test in there as well. And also don't forget this class closes out in October. And so, you don't want to, take the stuff too light, but make sure you stay on top of your assignments. Currently should be 2 tests posted. Yep, test 1 and test 2. Chapters 1, 2 is first test. Chapter 3, 4 is second test. So you should have access to both of those. So make sure you do see them. And then yeah, and so that's it for chapter 5. Next class we'll be looking to get into chapter 6. Also, if you guys have questions, make sure you bring them to class. Every day is opportunity for questions. I'll make sure that I leave room, after lecture during class time for you guys to ask the questions if you have them. If you don't have them and you're all good, then it's all good. But just want to make sure, we understand that as well. All right. Anything else? Or I want to say anything else? Anything before we close out?
Professor, I did have a question. So
Yes.
we are now responsible for test 1, chapters 1 and 2, because we're on chapter, this was 5.4, or this
Mhm.
is,
Mhm.
okay, so are we to do everything like chapter 1, pre-test, post-test, and review?
Well, let me do this. Hold on.
And
Make
then
sure.
would that go all the way up to chapter 5 as well?
Yeah, let me go into your assignments and then show you. Just make sure everybody's clear on that. Good question. Good question. So go into your main screen, hit on homework. So you guys should see all of this, of course. So as
Yes.
far as homework is concerned, we're up to right here, 5.4. These test reviews, they're not mandatory, but if you do them, 5 points added to your test if you get 85 or better. Now, when you talk about your test, the only test, okay, test 2 has not been posted yet, so I'll post that. I thought it was posted already, but you should see test 2 down here. It'll be right under here under test 1. Now, these pre-test, post-test, these I cannot remove, but notice it says sample tests. So you don't do any of those. So as a matter of fact, let me do this real quick. So we have make sure we see the same things. All right, so when you click on test, you should see test 1 and test 2 now. And those are the only tests that you have to do. Pre-test and post-test, this stuff down here, they're not my items. I could not remove them out of the math lab shell. So it's just test 1 and test 2 right here.
Okay, but the review quizzes were the extra credit.
Yes, so when you go, and they're under homework, they're created as homework, so you can do an unlimited amount of tries.
Okay.
So yep, they're in the category of homework. All right. Anything else? Anybody else?
Do we have any quizzes?
No, just homework and tests.
Okay.
Mhm. All right. Anything else? Anybody else? Everybody good?
For those assignments, I was kind of like confused. How are those?
Right here?
Yeah.
Don't do them. Normally I do those in a 16-week class. We have time wherein I can just say, do this time, make sure you're good or whatever, but we have enough work in this 8-week class that I just didn't delete them from my last shell.
All right, cool. Thank you.
Mm-hmm. Anything else? Anybody else? All right. So you guys are good. I'm good. I will see you next class. Have a great weekend. Be safe. If you have questions, bring them to the next class and we can knock them out. If you need to meet with me outside of class, shoot me that email so we can set it up. Other than that, you guys have a good one and I will see you next class.
Thank you. Take care.
Thank you.
Thank you. Thank you. Take care.